interacting too strongly with its environment, it typically doesn't have a definite position. Typically it's spread out over many positions. This is what's called a quantum superposition.
Quantum objects behave as if they can be and they can do several things at the same time. Electron can go through two different slits at the same time. This reminds me of Yogi Berra, who said, when I get to a fork in a road, I take it.
These radical ideas showed just how much quantum superpositions challenge the classical notion of reality. But these ideas troubled many scientists, including Erwin Schrödinger, who realized that if superpositions could be amplified to the everyday world, they would lead to bizarre predictions. To illustrate this point, he conceived a Gedanken experiment.
A Gedanken experiment is a thought experiment, that is, an imagined scenario that helps us to focus on some conceptual issue. If you really understand a theory, you should be able to say what the theory predicts in all sorts of situations, including some that can't be carried out in an actual laboratory.
Schrödinger's famous thought experiment has come to be known as Schrödinger's cat.
Schrödinger's cat is kind of a parable about the idea of quantum superposition.
Schrödinger was disturbed by the implications of quantum theory.
Apparent paradoxes in quantum mechanics.
He wanted to show how absurd quantum mechanics is.
He came up with Gedanken experiment.
The thought experiment.
This was the idea. You take a cat.
A cat?
A cat.
An unfortunate cat.
And you put it in a box.
Completely isolated from everything on the outside.
In this box as well is a hammer and a beaker
Filled with cyanide.
And there's also a control mechanism in the box, which is controlled by a single atom, which can radioactively decay.
Now, when the atom decays,
The detector activates the hammer.
the vial will be broken
The cyanide will be released.
And that is going to kill the cat.
and the cat will die.
And if it doesn't emit the particle, the poison is not released and the cat is alive.
Now suppose that after, say, an hour, there's a 50% probability that the Geiger counter will have detected something.
Until we look inside, the possibility exists that the cat is either alive or dead.
And if we believe quantum mechanics, then the cat at that point is in a state which is simultaneously dead and alive.
Schrödinger's point was that it's absurd to think that the cat is somehow simultaneously dead and alive just because it's described by a superposition. And so similarly, we should reconsider how we think about electrons in superposition.
One answer you could give is to refuse to answer the question. You could say, well, quantum theory is just a set of rules for making calculations to tell you where you're going to detect light, and that's all. This is a so-called shut up and calculate school. All these different sorts of answers have been given by different physicists. There's no general agreement, and it'll probably be a long time before there is.
Now, while physicists can disagree about whether to take this idea of the cat being simultaneously alive and dead seriously, the important point is that superposition cannot be explained away in terms of familiar classical concepts. And this is exactly what makes quantum mechanics so intriguing.
Like Schrödinger, Einstein continued to be puzzled by this apparent paradox.
Einstein felt that everything could be understood if only a deeper theory could be discovered, one which was more complete. To make his point, he came up with a new Gedanken experiment with his colleagues Boris Podolsky and Nathan Rosen at Princeton. They showed that certain combinations or superpositions of particles could combine in a bizarre and counterintuitive way that could not be explained by classical mechanics. The result is what's called the Einstein-Podolsky-Rosen, or EPR, paradox.
The thesis itself was somewhat difficult for the layperson, and perhaps even for scientists, to understand.
Ready? Okay. In a complete theory,
An element corresponding to each element of reality.
A sufficient condition for the reality of a physical quantity
is the possibility of predicting it with certainty without disturbing the system.
Then either one, the description of reality given by the wave function in the quantum mechanics is not complete,
Or two, these two quantities cannot have simultaneous reality.
One is thus led to conclude that the description of reality as given by a wave function
is not complete.
So what does this fairly dense statement mean? According to quantum mechanics, it's possible for two particles to be so tightly intertwined that they form a single system in which neither particle has a quantum state of its own. What Einstein, Podolsky, and Rosen said is, okay, let's take a pair of particles like that and separate them very far, maybe light years apart. Then imagine an observer over here measuring particle A, and thereby giving it a state which it did not have before. The key point is that when that measurement is made, it also determines the state of particle B, a state which, according to standard quantum mechanics, did not exist previously. For Einstein, this was impossible. How could a measurement over here affect something instantaneously that's light years away? So he and his collaborators concluded that the state of particle B must have existed previously, and therefore that quantum mechanics was incomplete. The idea of making a measurement over here and having it change something over there is what Einstein would have called spooky action at a distance.
Einstein believed that the world should be ultimately knowable, that there should be a reality out there. And quantum mechanics defied that. It didn't work this way. Einstein did not like that. That sparked his comment, God does not play dice with the universe.
Many early quantum physicists, including Einstein, hoped that a deeper theory would be free of the apparent contradictions of quantum mechanics. Some scientists hoped that the weird quantum elements were just going to go away.
After Einstein had introduced in 1935 the concept of what he called spooky action at a distance, it was the Austrian physicist Erwin Schrödinger who named this phenomenon in German Verschränkung and in English entanglement. The point is that Verschränkung is a better way to call this. Verschränkung is something like this, a very strong, well-defined connection. While entanglement sounds a little like spaghetti, not very well-defined.
Suppose we think of two entangled particles as a pair of dancers. If the dancers can't see or talk to each other while they're dancing, it is possible, though difficult, for them to remain in sync. They can do it only if they've pre-rehearsed which dance moves to follow and so on. Einstein hoped that the properties of entangled particles could be described in the same way, that the correlated way in which the two photons react to any possible measurement could be explained by having the measurement results predetermined. But Einstein was wrong. We now know that entanglement is a connection between particles that's stronger than any that can be shared using classical physics.
These quantum curiosities, of which entanglement was the oddest, puzzled researchers for over a quarter of a century. In 1964, Irish physicist John Bell designed an experiment to actually test what Einstein thought was impossible.
The Einstein-Podolsky-Rosen paper of 1935 was basically ignored for the first 30 years of its existence. Then John Bell came and showed that a basic, simple explanation of entanglement is not possible. This gave rise to fundamental experiments where people wanted to know, is nature really that crazy? Is nature really that strange?
John Bell's paper on entanglement coincided with the development of the laser, which made these experiments possible.
When I read the paper by John Bell, I discovered what entanglement was. And this was absolutely fascinating. Reading that paper was a shock, something like love at first sight. You know, this paper was explaining us that the big debate between Einstein and Bohr about the foundation of quantum mechanics could be settled by doing an experiment. I was an experimentalist. I wanted to participate to settling that debate. The basis of the experiment is to produce pairs of photons which are going to fly in opposite direction. And then, when they are separated by 12 meters, to make measurement exactly at the same instant. And the idea is that the two measurements, separated by 12 meters, must be separated in the sense of relativity. What do I mean? I mean that what I measure on one side should not be able to influence the result of the measurement on the other side. This is a critical point. special relativity tells us that nothing can travel faster than light. So it means that what I do here has no time to flow to the other end of the experiment. And for that, it was necessary that I could change the orientation of my polarizers in a few nanoseconds. Achieving this was a crucial and new part in my experiment. And what I did was to measure the polarization of each photon. Photons can be vertically or horizontally polarized, or polarized at 45 degrees. Now, a pair of EPR entangled photons is simultaneously vertically polarized and horizontally polarized. This is pretty strange, as strange as the Schrödinger cat, which is alive and dead. And now the question is, what is the result of the measurements? And in this strange situation, I found what was predicted by quantum mechanics, which is that whatever direction of measurement on one side, if I choose to measure along the same direction on the other side, I discover that both photons look aligned along the same direction. This means that the results of the measurements are strongly correlated, more correlated than any conceivable correlation in classical physics, in the classical world. It means that when the two photons are separated by 12 meters, they still behave as a single whole object. Einstein thought this was not possible, because it would mean that there is a kind of spooky action at a distance between the two objects. But if we want to reconcile the result of the experiment with an image we want to build, we have to put the spooky action at a distance in our picture.
Einstein never really understood the fundamental difference between classical and quantum theory. That is why he found it so difficult to accept things like the uncertainty principle. But quantum theory agrees with observation. God really